Yeah, so let's get going. Welcome everyone to the edition of the Physical Review Journal Club. I'm Nikhil Karthik. I'm an associate editor for Physical Review Letters. Today we highlight a paper titled First Direct Observation of Collider Neutrinos with FASER at LHC, which appeared in the July issue of the Physical Review Letters. Today's talk will be presented by Florian Bernlochner, and his colleagues from the FASER team, which made this observation. The talk will be, after the talk, it will be, the floor will be open for moderated discussion, which will be led by Professor David Salzberg. Just to introduce David, he's a physics professor at the University of California, Los Angeles, where his current research is on proton collider physics with the CMS experiment at the LHC. Previously, he has worked on fixed target neutrino experiments and building neutrino telescopes using the radio technique. Before we start, I just want to say a few words about PRL and what we're doing. PRL, as you know, very well know, that we have been publishing important and landmark papers over the entire spectrum of physics for the past few decades, a lot of decades, sorry. This is perhaps best illustrated by the fact that the Nobel Committee has chosen to cite PRL in the last 12 consecutive years in physics and chemistry Nobel Prizes. To this audience, perhaps what might pop out is the 2013 Higgs boson discovery paper, Nobel Prize, and the 2015 neutrino flavor oscillation paper. Though this talk might be on the fundamental physics aspect per se, but I just want to point out that physics, the PRL is now open to applied physics, and also we are quite welcoming to papers from astronomy and astrophysics that our readers might be interested in following. Perhaps even better testament to the position that it's held by PRL in the community of physics, maybe more than Nobel Prize, is that we are featured in the volume of you can see the volumes of PRL being featured in the Big Bang Theory episode. So I would be curious to know from David more about it, or he can tell us more about it. So before giving the floor to David, I just want some quick details about Zoom. Please keep yourself muted throughout the talk. The mute button is on the left-hand corner of your Zoom toolbar. So in the end, if there are questions, please use your raise hand button in your reaction icon in the toolbar. And then David will call out people to ask questions. If you have questions during the talk, please leave them as chats in your the chat button, and we can get back to it as in the later question part on the end of the discussion section of this journal club. So with this, I hand over the thing to David. Please go ahead, David.
Okay, thank you, and thank everyone for joining. Can you hear me? Okay, good. So please allow me to introduce our panelists from FASER. We have Florian Bernlochner, who will give the talk momentarily. Florian is a professor of experimental physics, particle physics at University of Bonn, working on neutrino physics with FASER and flavor physics with Bell 2. We have Tobias Bach. Tobias studied physics at KIT in Karlsruhe, Germany. Currently, he's doing his PhD at the University of Bonn, Germany, working on FASER tracking and neutrino analysis using their electronic detectors. Felix Kling is currently a research fellow at the DESY lab in the field of theoretical high-energy physics. For graduate school, he moved to the University of Arizona, where he worked on the phenomenology of extended Higgs under the supervision of Professor Shufang Su. From 2016 to 19, he was a postdoctoral researcher at University of California, Irvine, where he was involved in the original proposal of the FASER experiment. And from 2019 to 21, he was a postdoctoral researcher at SLAC. And during this time, he contributed to the proposal for the Forward Physics Facility. we have Professor Jonathan Fang. Jonathan is a co-spokesperson of the FASER collaboration and distinguished professor of physics and astronomy at the University of California, Irvine. So we were about to start the talk. I will ask Florian to begin, and I will put a link to the talk in the chat in case anyone wants to follow slightly asynchronously. So please, Florian, we look forward to your talk.
Thank you. Let me share the slides. Okay, I guess you can hear me and you can see the slides. Okay, then yeah, thank you very much for the kind introduction and the possibility for us to highlight our paper. Before going into the physics, I just want to point out that this is a big collaboration paper. So 87 authors contributed and helped building the experiment that I'm going to talk about. So it's not just me and the panelists, but really it brings together the effort from many, many people. Yeah, and none of this also would have been possible without the kind support of our partners down here that yeah, made it happen. Before jumping into the talk, I want to spend a little bit of time looking at the nice picture that you can see here. So you can see here the Large Hadron Collider, where protons are collided at the highest human-made energies today. And on the left-hand side in this small tunnel, you can see actually the FASER experiment where we made this exciting measurement for the first direct observation of collider neutrinos. And you can see it's a bit angled downwards, and I'm going to tell you in a second why that is. Okay, so as you all might be aware that the LHC is the highest energy collider in the world that is currently running. And it has 4 large-scale experiments and several small ones, and most of them are really designed to search for heavy and strongly produced new particles at high transverse momentum, where transverse here is with respect to the colliding beam. And the design of those detectors really is optimal for those things. So at high transverse momentum, you have precision tracking possibilities and other things. But what you miss out on is that you produce an immense number of light standard model hadrons at low transverse momentum that essentially exit the detectors without being seen in the forward and backward direction. Many of those standard model hadrons decay weakly and then produce a very intense neutrino beam, which is very interesting in its own right, as you will learn in a second. There's another thing that is quite interesting. So you might also be able to produce weakly coupled light new particles with long lifetimes that you can't see in the large scale experiments that you could study if you just could instrument this region there. Just to give you a house number, so if you would want to study just 1% of all pions that you produce in proton-proton collisions with 10 GeV in the forward direction, you only would need to instrument 10 to the minus 6% of the solid angle, which is tiny. So if you could place a small detector in this region, you would have impressive sensitivity since you produce so many of those light standard model hadrons. And that's where FASER comes in. It's a small, inexpensive experiment at LHC with the goal to search for long-lived particles and to study collider neutrinos. You can't really place a detector right at the end of the big large-scale detectors because you have the beam that has to go into the collision point and also go out. But what you can do is you can place a detector far, far away, but in the line of sight of the collision point. And this is exactly what FASER is. So FASER is placed about 500 meters away, though, in the line of sight of the collision point, but shielded by the LHC magnets that push away a very large fraction of the charged particles that you produce in the initial collision, and also shielded by about 100 meters of rock and concrete to make sure that you have a low background environment. And all of that, though, still in the line of sight of the original collision. And this is nice because this also maximizes the neutrino flux that you can observe in your detector. You can also see at the bottom here an aerial shot of where the FASER detector is located with respect to the Atlas interaction point and the cavern. Okay, let me quickly run you through the detector from front to back. So this is a render of the detector. And for instance, neutrinos or other things we want to study would enter here from the right-hand side, where also the Atlas interaction point would be. And then the first thing a particle would encounter when entering from the right-hand side is the front scintillator veto, which is made out of 2 layers and is very, very efficient so that you can veto charged particles that would traverse your detector and would be mainly our backgrounds. Right after that, you have the FASER emulsion detector, which is made out of 1.1 tons of tungsten. That doesn't sound like a lot, but if you have high energetic neutrinos, they have quite a large interaction cross-section. So even a small 1.1 ton detector actually can produce a large number of interactions that are interesting to study. Right after that, we have an interface tracker, a scintillator reader system, and then a decay volume in a magnetic field, where we can reconstruct charged particles with 3 tracking stations. And since it's immersed in a magnetic field, we actually can make a statement about the momentum and also the charge of charged particles. And then at the very end, here in red, is the electromagnetic calorimeter, where we also can study neutral particles, but that's not relevant for the analysis here. Okay, so we started recording data in 2022, and there we recorded 35.4 in Merz femtobarn. We roughly doubled that data set by now, but the data that I'm going to talk about is just this 2022 data that we analyzed. Okay, so why should you care about studying collider neutrinos? Just to put this a bit into historical context, so prior the FASER result, not a single neutrino produced in a beam-beam collision at a particle collider has ever been directly detected. And that's not due to their small number. There's a large number of neutrinos that are being produced. It's just it's very challenging to instrument that forward region to actually make an observation. The energy of those neutrinos, which we produce at the Large Hadron Collider, is in the TeV, which are the highest human-made energies. And since the interaction cross-section actually increases with the energy, it's most likely that you actually can, if you could build a detector there, as we did, that you would see high energetic neutrinos. Further, all flavors of neutrinos are being produced. So predominantly electron, muon, and tau neutrinos are predominantly produced by kaon, pion, and d or d sub s meson decays. So you basically get the whole palette of neutrino flavors that you could study. And just one general statement. So whenever we found a new way to study neutrinos from a new source, be it the sun, reactors, the atmosphere, we learned a great deal about not only particle physics, but about the cosmology or the universe or better systems. And there's a lot of interesting measurements that can be improved if we study these collider neutrinos. To give you 2 more tangible things that we actually want to measure, one of the things that is quite interesting is to measure the cross-sections of different neutrino flavors in these large unexplored energies. And you can see here basically measured cross-sections for electron, muon, and tau neutrinos and the reach that FASER will have. So you can see that we can really push beyond of what has been measured. And with the exception of the muon neutrinos, there's basically no upper measurement or that FASER will reproduce. And for muon neutrinos, we can really fill this important gap between what can be measured by IceCube. Then the second thing is it really allows us to have a microscope into the proton by really disentangling where those different neutrinos came from, where they're produced by kaon decays and charms. And this is essentially encoded in the neutrino energy spectrum. So if you can measure the neutrino energy spectrum, you can really disentangle the production processes, which gives you really important insights into the large forward dynamics of proton-proton collisions, which have wide-ranging applications, for instance, in astroparticle physics, where you can then really improve models that allow you to do measurements better. Okay, so hope I convinced you that it's interesting to study collider neutrinos. So let me tell you how we can do that. So FASER has a dedicated emulsion detector, FASER Nu, with these aforementioned 1.1 tons of tungsten. And there's emulsion films in there that are interleaved with 1.1 millimeter thick tungsten plates, which you in principle could analyze. And what happens is if a neutrino enters here from the left-hand side, we would look for a so-called charge current interaction where the neutrino is transformed into a lepton. And since this is happening at really high energies, you also get the spray of particles from the charge current interaction that you can see. So this basically sets the scene of how we did carry out this first analysis. So we focused on the muon conversion, since the muon can actually then propagate through the rest of our detector, where it can be found and analyzed by the electronic components. And this has the benefit that we can study neutrinos and antineutrinos and actually distinguish them based on the charge of this muon. And we have a fast turnaround time, so we have to analyze basically recorded data, and we can provide a quick result. The drawback of all of this is you can only do this with the muon neutrinos, because the electrons, if you have an electron neutrino and do the same transition, they essentially get stuck in the emulsion detector. They don't make it out, and for the taus, the number of events is just too low. And it's based on this idea paper from these authors that proposed that we should look into this. The second way is, of course, the long way. You really make use of the emulsion films. You can scan and analyze the films. There you can study all the neutrino flavors. You have the excellent spatial resolution that allow you to do really precise measurements of the energy as well. But this is very time intensive, as each film needs to be scanned and analyzed. And we recently did actually this. This is a new result for the summer this year. And if you're interested, you can look into this conference note. But that's not how we first looked at collider neutrinos. Just to give you a little bit an idea, so if we only focus on muon neutrinos, we have about 10 to the 11 of them traversing the FASER detector in our data sets of 35.4 inverse femtobarn, and about 1,000 of them will interact in the FASER new tungsten emulsion detector that we can then look for them. And this is essentially what we're focusing on, as explained. Here is a little bit of comic that shows this. So you have a muon neutrino that enters the FASER detector from the Atlas collision point, interacts then in the tungsten here with a charge current interaction, undergoing on the quark level either one of these two interactions. And this is quite violent, to speak so. So there's a lot of energy that is transferred to the tungsten. So we produce a spray of particles that you can actually then see in the interface tracker, and then a muon that traverses the entirety of the detector that you can then study and find with the tracking spectrometer stations and identify. So how do we distinguish such events from other things happening? So what we do is we take the muon that we reconstructed and actually extrapolate it back to the very front scintillator, because one of the main backgrounds that we have is muons that also make it from the Atlas interaction point all the way down that half kilometer, and also make it through the detector. That would leave a very similar signature, but would send off a signal at the front scintillator station. And we only want to look at events where we are sure that we did really hit this front scintillator station. And with that extrapolation back, we then require that it has to fall within 12 centimeters of the center of the station, and that the muon really was a high energetic muon with more than 100 GeV, so that there was no funny bending. You can see this here in this figure. So this is the extrapolated radius from the center and the momentum, and essentially our signal region is indicated here in this box. If we require no hits in the Vito station, we find about exactly 153 events. And if you require one hit in the Vito station, you find 10 events. These are these 4 and 6, depending on where the hit was in the Vito station at the very front. And if you require 2 hits, you have these 64 million events that are just muons that made it all the way from the Atlas interaction point. Okay, so we have 153 events, and to make a claim that we are sure these are neutrinos, we have to think about what possible background contaminations could there be. And there's 3 of them to think about. The first one are front veto inefficiencies. So what if one of those muons that made it all the way from the Atlas interaction point actually made it through the front veto scintillator due to an inefficiency? We know from lab measurements that a single layer has an inefficiency of 10 to the minus 7. Which is very small, and we have 2 layers, so this should be completely negligible, but we still estimate this with a data-driven way. Then the second background are from neutral hadrons. You can imagine that you have a muon that comes also all the way from the Atlas interaction point, interacts with the concrete in front of our detector, produces a neutral hadron. The neutral hadron makes it into the detector and then leaves a signature exactly the same as for a charge current neutrino interaction. This we estimate with simulations, and we find with these simulations that in our 35.4 inverse femtobarn, about 0.11 events should have that origin. And the last background is from geometric muons, so muons that basically missed the front veto system, then scattered off in the tungsten target, and then also made it through. And this we estimate from data-driven control regions and estimate that contamination to be 0.08 events in the analyzed data set. You can put all of that together. So we have a background of about plus minus 2 events with uncertainties. And if you do a statistical analysis, you see that we found about 153 neutrinos with 16 sigma significance above the background only hypothesis. one thing we did after unblinding is we then looked at where we extrapolated back this muon track, because that's a really good proxy where the neutrino came from. And we wanted to make sure that there's not a single region in the scintillator where there would be dead material. And you can see here these black data points, which are all the 153 neutrino candidates extrapolated back to the front scintillator station. And you can see the dotted radius, which is the fiducial region we selected. And you can see they're really distributed, not in a single spot, but uniformly, roughly, which is what we expected. And the red dot is the extrapolated Atlas line of sight where the collision happened. There's two more fun things that I want to show you. One is you can also look at the charge of the reconstructed muon track. As explained, if there's a positive charge, you have an antineutrino. If you have a negative charge, you have a neutrino. And the way we usually plot this is as charge over momentum, because at really high momenta, it's hard to distinguish through the bending of the trajectory what charge you have. But you can see here a good separation, and we observe about 40 antineutrino events. So you not only see neutrinos, but also antineutrinos, which is nice. And the plot on the right-hand side shows you the momentum of the reconstructed muon. And about 80% or at least 80% of the original neutrino energy is passed on to the muon. So that's a really good proxy of estimating the neutrino initial incidental energy. And you can see that we see a lot of candidates that are way above the 360 GeV mark, where the previously highest human-made muons, muon neutrinos were recorded. Yeah, just one word. You also might have spotted, besides the data point, this histogram that's from the Gini simulation. The error bars, though, are only statistical only, so they don't include any systematic effects. So they're only there to guide the eye, so that you can see that this roughly confirms with, or it's roughly consistent with our expectation. Okay, let me show you an event display of one of those events that we saw. You can see here, again, a render of the FASER detector. You have the front scintillator here. There's no signal in there, so that's consistent with a neutrino. You see a lot of activity in this interface tracker that I mentioned from the remnants of the charge-current interaction that really violently knocked out a lot of particles towards the detector. They're stopped essentially by a LED block here, but about 57 clusters are here. And then at the very back of the detector, you can see the muon track here in red, showing a muon with 843.9 GeV in momentum, which is a good proxy for the incidental neutrino energy. So it's a really high energetic neutrino that made this. Okay, this brings me to the outlook. So we had this first direct observation, but this is just the beginning. There's more studies underway. So I already mentioned the emulsion detector analysis, where we, for the first time, also observed electron neutrinos with 5 sigma significance. And we're currently working on measuring the neutrino energy spectrum to turn this first direct observation also into neat first physics results. There's also a huge effort at CERN to continue this program into the high Lumi LHC era. The high Lumi LHC is planned to start taking data after the next shutdown, and the new facility is proposed to host a suite of such forward physics experiments that then can expand up on what FASER and other experiments are doing. If you're interested in that, here's a link to the forward physics facility white paper. Okay, then let me close with showing once more a picture of the entire collaboration. It is really a collaborative effort. Without the hard work of many, many people, this would not have been possible. And yeah, it was great, and we're really grateful to the kind support of all our supporters and the institutions that are backing us. Thank you.
Well, great, Florian. Thank you. Let's all hit a reaction to thank Florian rather than trying to clap over Zoom, which does not work. So hopefully there's lots of fun emojis showing up. Great. I was going to start with one slightly lighthearted question. I happened to come across a description of FASER over here, and I was wondering if anybody recognizes where that's from.
Well, I recognize it, David.
I do too, because Jonathan told me.
So people might remember that's the living room at the Big Bang Theory, and I put this up the day Jonathan Feng came to visit. They were talking about FASER. I had a question which I think you actually wound up answering, but let me just double check something. So when I was going through the paper, I was trying. You have 153 events. You were saying you were 16 sigma from background, which of course is sort of Gaussianizing the probability, which is fine. And your total background, if I understand, is about 0.2. And that with the back, and what I hadn't understood was that the leakage through the veto was negligible from the paper. So thank you for clearing that up. So do I understand that you're saying 0.2, the probability for 0.2 to fluctuate to 153 is 16 sigma, or are you including something else in that?
So the indeed we are Gaussianizing our background uncertainty. So the and the estimated actually number of background events is even lower, but the errors on them are about 2 events if you then go up and down. And we're using one of those LHC one-sided discovery statistics, and then the asymptotic approximation. So it's really hard to test this with toys, as you can imagine, because 16 sigma is so high. But if you chuck this into the asymptotic formula of that test statistics that is penalizing negative fluctuations, which here is a little bit silly because you have so many positive events, you get those 16 sigmas. Yeah.
Anyway, that clarifies it for me. I knew it was 153 events, and I didn't know on exactly what the total background was, so I can summarize it as less than 0.2. So we had one question that came up, and I see a bunch of hands. People, I'm going to call on questions from people putting them in the chat. That's great. We'll start with Dennis Doran, who asked a question. So Dennis, if you would show your video if you're able to during your question, we won't force you. Go ahead, please.
Yes, since you use the emulsion process to look for the electron neutrinos, I'm wondering if you saw any oscillations in the middle of the emulsion. And if not, is that a viable possibility in the future?
So the emulsion analysis actually a very small number of events. And if standard model holds, I don't really expect the neutrinos produced at the Atlas interaction points to actually oscillate. If there's some new physics, we do, but yeah, maybe, I don't know if Felix or other people of the panel that know a lot more about that aspect want to jump in.
Yes, what you said is correct. In the standard model, we don't expect neutrinos to oscillate because the energy is so large, the baseline is relatively small. In principle, one could imagine new physics that would give us oscillation of exactly the right length scale. And that's something that we plan to look forward to in the future. But yeah, that probably takes some time until we have the sufficient statistic to actually probe these scenarios.
So I think the way we would see that essentially is you need to measure it differentially, and then you can basically check as a function of the neutrino energy if you see a deficiency with respect to the expectation that you would normalize to another energy range, and then you can make a statement like, there has been a weird oscillation which we don't understand. There must be new physics doing that. Yeah.
Okay, thanks a lot. We have a few more questions. We have Robert Gristo, from editor of PRL, gets to ask a question.
Actually, I have 2 questions. One of them is a little cheeky, so I'll start with the scientific one. So I guess you don't have to do a veto for atmospheric and astrophysical muons because the energy is so high, and there must be some small tail, but if the flux is too low to worry about that.
Yes, so but we nonetheless, we require that the signals we see are consistent with a bunch crossing ID, so that we only look at collision events. But since the detector is so long, there's a really small fraction that actually could make it through, and then yeah, it's a long tail. Yeah, I don't know if Tobias, if you want to add something to that.
Yeah, actually, we were looking for this also because we installed the detector already in 2021 and started data tech in 2022, and in this 1 year where we didn't have any physical collision, we also didn't see any event which would have then come from cosmics or muons or whatever, which went through the whole detector. So I think it's safe to assume that also during the data taking period, there hasn't been such event.
Sure. All right. So my cheeky question is, why did you wait till 16 sigma?
Well, we wanted to be sure. No, we were moving as quick as we felt comfortable. Yeah.
Thanks. So we have a question from Sri Valori. Sri, would you like to ask your question, please?
Yeah, firstly, let me congratulate all of you for the great work you have done. And my question is, would you be able to observe massive neutrinos at some point later in your work?
So I think there is sensitivity to do that. Yeah, I don't know, Felix, if you want to jump in.
Okay, yeah. So there are, depends on how massive. So if they are just a bit more massive than our standard model neutrinos, then there would be a small mass difference. That means that would lead to an additional sort of oscillation. And we could see it in the energy spectrum of those neutrinos. We would see some oscillation patterns that we could then use to probe those. If they are very heavy, they could actually be metastable, so they could decay. And Florian hasn't really touched on it, but he mentioned that the FASER detector is a detector to look for the decay of long-lived particles, and we could see such decaying heavy neutrinos in this detector. So yes, we can in the future, but again, we need a bit more data to test those scenarios.
Thank you very much.
Excellent, thank you. We had a question from someone with the handle Digger about the emulsion films. Would Digger like to ask the question out loud? If not, the question was, what is the frequency at which you change the emulsion films, which I guess is an issue because they'll slowly be getting exposed and starting to have overlapping events and cosmic rays and so forth.
Yeah, so we swap them out about every 30 inverse femtobarn. I can maybe quickly share something. So for the initial data taking in 2022, we actually swapped them out 3 times. You can see here the date. So and they covered between 9 and 28 inverse femtobarns. And if you would wait too long, the track density just gets too high, and then you can't do the analysis you want to do because you don't have any time resolution, right? So you basically just have to film, and then you need to analyze it to find traces of neutrino interactions. Yeah.
Okay, so we have another question from Bijan Gangopatihai. I'm sorry if I mispronounced that. Do you want to ask your question, please?
Yes, sir. My question is, does this experiment throw any light on dark matter?
It might. So as explained, so we can look for very long-lived particles. So there's many extensions of the standard model with light dark matter candidates that predict, for instance, the existence of dark photons, which is one of the poster child particles that we can constrain in terms of coupling and mass. So yeah, so we hope in our entire data set that we can look for that. There has been a preliminary result that I also linked in the talk where we set limits on dark photon production.
Thank you, sir.
Maybe I can ask a related question if I could jump in. It's about your decision to put an emulsion target in your experiment. I understand that for the electrons, they don't leave the volume, but there's other techniques like TPCs or something that could be used. So typically people use emulsion when they really need a very fine displacement sensitivity. So was there some dark matter model or supersymmetry model or something like that which led you to choose emulsion as your active medium as opposed to one of the other detector technologies?
Don't know if Jonathan or Felix want to jump in.
I could say a few words. So as you've seen, so this talk was all about the first detection, which was muon neutrinos. Then as Florian also mentioned, we have just recently put out a paper detecting electron neutrinos. But then there's still, of course, the third one, the tau neutrinos. And so that is actually a big target of the FASER program. And that's a large reason why the emulsion will be really useful, right? So we have at the LHC huge energies, which is great. So that means you can have a new tau come in and actually make the tau, even though it's quite massive, 35 times, well, anyway, much heavier than the muon. So we benefit from that huge energy. And so what we'd like to do is be able to see new taus come in, create taus that then propagate a little and decay. But the little is very little. And so that's exactly where the emulsion spatial resolution will be very helpful. And so that's one of the drivers for this. And we expect actually by the end of run 3, which is in a couple of years, to see maybe as many as 50, 70 tau neutrinos, which is not a lot, but it's a lot compared to what's been seen so far. The whole world supply is roughly somewhere between 10 and 20. So we'll maybe triple that supply. And of course, that will bring in all sorts of new interesting studies. So you can do lepton universality, checking that things are the same across all 3 generations, as opposed to just the first 2. And maybe there's some new physics that shows up predominantly in coupling to heavy particles like taus. So I think that's probably the main motivation for the emulsion detector was the tau neutrinos, but that's yet to come.
That makes sense. And so it would be sensitive to what we call high tan beta supersymmetry, for example.
Yeah, I guess it could be. Yeah, there's a number of BSM models that can sort of, mess around with the 3rd generation and not touch the first 2. And so I guess from a theorist point of view, it's always sort of the last resort of scoundrels to take all the new physics and dump it into the 3rd generation where no one can see it. And so this will basically flush out that possibility.
Okay, so we might move on to some. It looks like we have a few questions that are getting a little bit beyond the FASER itself, but could be interesting to talk about. So maybe we'll start with Yoshio Matsuki. Yoshio, would you like to ask your question?
Yes, thank you. First of all, congratulations for the successful experiment. It's very good. You produced neutrino and detected directly from the chamber. It's very good. It means that you can create some information and then you can detect it in some way. I'm a mathematician and then I work with the gravitational field with the Riemannian geometry. And then I calculate a lot. I publish a lot about this and the black holes and so on, dense stars and the information from those things. And then I believe that there should be some information. And the neutrino and gravitational waves are both messengers from cosmos and stars. So I believe that neutrino also should have some information bringing out from the deep space or somewhere to us. Your opinion, please.
So one thing that our measurement will help doing is it will help improve measurements of air showers and also of basically large experiments that are looking for neutrinos coming from the cosmos. So in that sense, if you then do maybe combined analyses with gravitational waves with those sources, there might be some direct impact. Otherwise, I'm not sure there's another connection from the neutrinos we study with that. But yeah, maybe someone else from the panel wants to jump in.
Maybe let me.
Please.
So yeah, our neutrinos come, of course, from Atlas, not from the cosmos. So we're not probing directly. But the way that our neutrinos are produced is very much similar to maybe how they are produced in the cosmos. Like black holes produce jets, really speed up particles that then collide and produce cosmic neutrinos. And or protons hit the atmosphere and produce atmospheric neutrinos. And there are very sizable uncertainties in these simulations. So how can we understand these processes? And the best thing is to, well, collect data and understand it. So look at collisions at the LHC in a controlled laboratory environment and understand neutrino production there. And that will tell us how these neutrinos are produced in astrophysical environments or the atmosphere, and extends our understanding and sensitivity to other physics effects there. So there's a deep connection to this field.
Thank you. I really appreciate your comment. Thank you very much. Good luck.
There was just a practical question. I think it's answered in your paper, but it's probably a quick answer. Is how long was this exposure that gave you the 153 events? It looked like it was 1/2 of one run at so a few months at the LHC, right?
I think it's Tobias will know, but I think it's June to November data taking or in 2022.
Yeah, I think we excluded the first few weeks since we basically started the detector and all of this. But yeah, July to November.
Okay, so by the way, Robert, did you want to ask another question?
Sure. I did have one question. So I know that with the planning of muon colliders, there's the worry about the neutrinos that they produce. And I wonder if anything you've learned from FASER talked about how you could monitor that, or whether there would be potentialities about that. So, you're going to get way more neutrinos from a muon collider. Have you thought about what FASER would teach us about that?
Yeah, it's a good question. But I think, I don't know, Jonathan or Felix. So I have not thought about it. So there are some direct applications of what we're doing for, I don't know, the next 100 TeV Hadron Collider. But for the muon collider, since the production process is very different. Yeah.
I mean, I think maybe there's two aspects to the question, Robert. So one, in terms of, it's a serious question, which is whether the neutrino radiation can be a threat to people on the surface of the Earth, right? And that's been thought about. And I think, and part of the reason that is especially relevant for the muon collider is, of course, it's not a perfect circle, right? It's a kind of a racetrack with some straight sections. And so then you sort of preferentially have a much larger flux in the direction where that straight section goes when it propagates out of the Earth. So I think, I'm not sure we have a lot to add to that, because people have thought about that and have thought about pointing the muon collider at a slight angle so that it takes a long time before that sort of beam comes out of the Earth's surface. So it sort of spreads out the flux quite a bit. But one aspect that definitely has implications is that, this sort of experiment is sort of, well, in this case, completely parasitic to the LHC, obviously, because no one had thought about this when the LHC got going. And even after it started running and discovering the Higgs and everything, this wasn't even sort of an idea that people had thought to make into reality. But now, given that, we're getting some nice results, it does have implications for future colliders, because you can basically add a detector like this, or more generally, we're calling it the forward physics facility, onto any future collider. Certainly, future hadron colliders, like the 100 TeV proton-proton collider, which is being discussed. but also lepton colliders. So the ILC, there are now some nice studies talking about what you can do when you have a linear E plus E minus collider and you treat it basically as an extremely high energy electron beam dump. And then finally getting back to your question, the muon collider, there are also studies about that, using the muon collider as sort of a source and putting a forward physics facility there. And the results are astounding. I mean, you can probe a whole bunch of new physics scenarios with incredible sensitivity just because you have a very, very high energy, parton interaction with the muons, and also very high fluxes. So I think one sort of lesson for the future of colliders is that, when you're building these extremely expensive and large things, putting a little add-on of this sort of forward physics detector is typically an extremely good investment for the amount of physics you get for it.
Thanks. We have one more detector question from Harkarat Verma. Harkarat, would you like to ask your question, please?
Yeah, sure. Thank you for having me, and thank you for having this discussion. I just wanted to ask, is there anything besides increasing the spatial resolution that you guys talked about that could help in observing more tau neutrinos? And I think someone talked about neutrino oscillations and how spatial resolution would be the main factor by which you can't see them right now. And so would increasing spatial resolution help us in observing more neutrino oscillations in this experiment?
Yeah, so one thing that we could further investigate is how we identify the tau neutrinos in the emulsion film. So you could think of investigating their, for instance, new deep learning algorithms that can maybe better isolate them from the large track densities we have there. Yeah, otherwise it's basically limited by the number of passive material we have in there. So if you could increase that, of course, you would get more tau neutrinos, but that's not foreseen. Yeah. Don't know if other members of the panel have some deeper insights.
Maybe some more trivial addition. So with the emulsion detector, well, we have the emulsion films, but in between we have tungsten plates as target. And we chose that because, well, it's very dense. So we can have a large mass in a small volume. And so actually this emulsion detector technology allows us to do exactly that. If we would have used a different technology, we might have to use a different material, which would have a much smaller mass at the end. So we see less neutrinos. So that's maybe a more practical side advantage.
Well, great. I want to thank everyone for all the questions. That was terrific, wide-ranging, lots of great details that we couldn't get just in the paper. So that's really helpful. And I want to thank PRL for arranging this chance to interact with the authors. And so let's thank the panelists again with an emoji, and then I will hand it back to Nikhil, who will close up our meeting.
Yeah, thanks everyone for joining today's journal club, and thank you, David, for being a great host for this. And yeah, so I just want to say, we have this journal club on a monthly basis, and I put a link here, and you can check for more details on the future things on the PRL webpage. And today's recording, the recording of today's journal club, as well as the ones in the past, you can find them here. I put it in the chat, in the link here. Yeah, thanks again. So this closes the meeting today, and I'm looking forward to meeting you again in another future edition. Thank you. Bye-bye.
Thank you very much.
Thank you. Bye.